Okay, here we go. So everyone, with this one, it says, right, this one always gets people, but you've got to know it, because it's the easy one to write. A recursive definition is the one that's just intuitive, meaning, what do you see happening? So we would say a sub n is equal to what's happening? Yep, previous term, and in this format, right, we write it, I thought most of you got it. A sub n minus 1 is how we state previous term in this type of notation, and then you said you're adding 2. True. Very good. I saw most of you got that. Now, here's the one thing you have to remember with this, and I always forget myself. Yes, that's all fine and dandy. Take the previous term and add 2, but let's pretend this wasn't here. You need to tell it where to start. You'd also need to say a sub 1 is starting at 2. Otherwise, it doesn't know, okay, where do I start adding 2? So don't forget that on the test. Here we go. Then also an explicit definition for arithmetic, you would have this memorized as a sub 1 plus n minus 1 times the common difference. So you said a sub n is equal to 2 plus n minus 1 times 2. And then, yes, I would want you to simplify because in summation notation it's simplified. So when you multiply that in and combine like terms, you would get 2n. Right? Any questions on that? Sweet. Let's ace that part of the test. Okay, erase your whiteboards, try another one. So what I want you to do in this one is find the sum by hand. And then for fun, let's practice writing it in summation notation. And then we'll learn in a second how to type it into your calculator. Go. Let's go through it for the video. So good. I heard some of you explaining it to your neighbors, which was awesome. First of all, we know this is a sub 1. This is sum a sub n. If we knew it was a sub 12 or a sub 20, we would know we're summing up 20 terms. N is the number of terms we're summing up. So I heard these guys over here talking to each other, and they said, well, let's use the explicit formula. A sub n is equal to a sub 1 plus n minus 1 times d, and go ahead and plug in everything we know. 22 is equal to 2 times n minus 1 times 2, and then they solved for n, correct? So they subtracted 2, so they got 20 is equal to n minus 1 times 2. And then I can multiply 2 in or just divide by 2, right? Divide both sides by 2, we get 10 is equal to n minus 1, so isn't n 11? So now that was a sub 11, which is very useful because now we can do this formula. The sum of 11 terms is equal to 11 divided by 2 times a sub 1, which is 2, plus a sub n, which is 22. And you got what? Awesome. And then right here in summation notation, you said I'm taking the sum from what? 1. Now, why do we use 1? Because we called this a sub 1. So 1 to 11, right? And then our explicit formula in here would be 2n, right? Everybody good? Okay, let's try another one. So actually, let's just do this one together here. So it says find the sum by hand and then by calculator. So I'll show you how to do it in your calculator. Now, one thing I want you to notice is in summation notation, we have a linear equation here. That means it's arithmetic. The only way we know it's arithmetic is if it's linear. All right, so now by hand, we would have to say because it's arithmetic, we'd use the formula S of n is equal to n divided by 2 times a sub 1 plus a sub n. Here we go. How many terms are we summing up? No, everyone's wrong. 7. The first thing we would plug in is a 4, correct? Then 5, 6, 7, 8, 9, 10. Isn't that what we're plugging in? So, yes. The top minus the bottom, 10 minus 4 is 6, plus 1 is 7. So we're summing up 7 over 2 times a sub 1. A sub 1 just means the first term you're summing up. You plug in your lower limit. So 2 times 4 is 8, plus 3 is 11, right? And then plus a sub n. A sub n is the last term you'd be plugging in here, so 23. And there we go. Type it in. We get the sum is equal to... What? Hey, now let me show you how to do it in your calculator, because a lot of people say, well, why go through all the trouble of taking this to summation notation format? Well, it's because if you have it in summation notation, you can check your answer by calculator. So everybody, some people's calculators are more advanced than others. Like, for example, some of you with the updated software can hit max 0, and it will pull up a summation sign, and you just type it in, and then hit enter. But most of us have the old school calculator, so let's show you how to do it with the old school calculator. Sweet. So, oh crap. Okay, let's see here. Pull up your calculator, everybody. So what you're gonna hit first is you're gonna hit the second stat key. Second stat. The hardest thing is remembering where to go. Second stat, go over to math, and then go down to the sum. We're trying to find the sum. Hit enter, then hit second math again, second stat again. Go over to, instead of going over to math, go over to ops, down to sequence. We're finding the sum of a sequence. Then you'll type in the equation. So our sequence was 2x plus 3, wasn't it? 2x. So sweet. In your expression, type in 2x plus 3. And then put a comma sign. For us, we're putting a comma. For some of your calculators, it's setting you up. It's just making your life easier. It's going to do the commas for you. So the next thing says variable, right? Type in x, because we used x. And the next thing will say lower limit, which was 4. And then the next thing would be our upper limit. So comma, upper limit was 10. Then I'm going to close my parentheses. A lot of your calculators, like I said, it will have it split apart and just prompt you to do these things. Just ignore the step. Just hit enter. And we get 119. Unless your calculator is the updated version, you probably can't. Okay, I'll help you at a different time. No, mine's a T80 4 plus, and this software is not updated. Okay, cool. Well, that just makes your life easier, so that's good and dandy. Okay, so that's how you can check your answers, right? Even if I say do not use a calculator, use the formula, that's a great way for you to check your answer and then say I've done something wrong or I'm doing it right by hand. Okay, all good. Yes. So some of you might wonder, like, where did this summation formula come from? So, you know, over the years, this story's been told, and so there can be some flukes in the story, but as the story has been told to me, what happened was a really interesting story. So back in the day, I think his first name's Frederick, but last name Gauss. He was 9 years old and in a math class. On that day, the teacher kind of wanted to relax and hang out, and keep in mind they didn't have modernized calculators, right, or cell phones or things like that. So the teacher said to the students, I need you to find the sum of 1 through 100, and it's going to take you a while, so don't talk to me, and you guys work on that. So Gauss got to work, and within about a minute and a half to 2 minutes, he arrived at the answer. He's a 9-year-old boy. So the teacher's kind of like, what the heck is going on here? Somehow this kid is either cheated or what's going on. So he kind of said, well, how did you get that? And Gauss said, well, it's really easy. I was writing it out and looking at it, and I noticed something. If I were to sum these up, 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. So he said, how many pairs of 101 is going to be here? 50 pairs of 101. So he did 50 times 101 and got the answer. He's a 9-year-old boy and saw that pattern. So it makes sense. So look, that formula makes sense. You take the first term, correct? The first term plus the last term, 101, right? And then how many pairs of 101 will there be? Half of the number of terms. Half of them. You're splitting this up into twos. So that's why it's 100 divided by 2 would be 50 pairs. Does everybody see where the formula comes from? Pretty cool. So obviously Gauss was a very smart 9-year-old gentleman. Okay, let's get to 3-2. I really like this lesson. This is the last lesson of the unit. It's awesome. So freaking cool. So everybody, 3-2, geometric sequences and series. It has a lot of similarities to arithmetic sequences and series. So everybody, you build a geometric sequence by multiplying each term by a constant number. In a geometric sequence, the ratio of any term to its preceding term is a constant value. So what these geometric sequences are going to have is what's called a common ratio. So for example, ratio means division, everybody. What's 81 divided by 27? 3. 27 divided by 9. 3. 9 divided by 3. So we were timesing each term by 3 to get to the next term. Does everybody agree? So this would be considered geometric. So we would say yes, because in your instructions it says, is this geometric? We'd say yes, because our common ratio was 3. It's got to be the same every time, just with arithmetic. It's got to be multiplying by the same number every time. Let's do number 5. Is this geometric or is it not? This divided by this is 0.5. This divided by this is 0.5. This divided by this is 0.5. Now, it would be appropriate in your answer, if it starts with decimals, to put your answer as a decimal. So we'd say, yes, it's geometric because we had a common ratio of 0.5. If you start with fractions, end your answer in fractions, but decimals, decimals. Now, look at the general formula here and make sense of it. You start with some value a, and that's our first term. Wouldn't our second term be a times r? Now think about it. To get to the third term, we now will have taken the first term and multiplied r 2 times, wouldn't we? And so on. So this is making sense, right? Okay, cool. What I want you to do is problems 1 through 9. All right. So now, just like similar to an arithmetic sequence, for geometric sequences, you can also write recursive definitions and explicit definitions. This is already on that handout I gave you, so you could just refer back to that. So a recursive definition is, once again, the formula that's really easy to write, the intuitive one. You look at it and say, you take the previous terms and do whatever to it. So look at number 10. Just for practice, let's write a recursive definition because you will be asked to do this on the test. So for fun, let's practice this. It says find the 10th term. Right now I'm just practicing writing a recursive definition. So we would say a sub n is equal to, yep, you take the previous term, a sub n minus 1, and aren't we timesing it by 2? Okay, so we would say a sub n minus 1 times 2. So easy. And then a sub 1 is equal to 2, for example. So the recursive definition is the one easy to write, but not so useful. Because if I said to you, find the 10th term, you're going to need the 9th term. So we might as well just do it all out by hand if you're going to try to use this formula. So that's why we would rather use an explicit formula, an explicit definition for geometric, which is this. A sub 1 times r, where r is the common ratio, raised to the n minus 1. So just to make sense of the formula here, let's write out an explicit formula, and then we'll make sense of it because it's easier to memorize here. Q to the x, and then what would you plug in for x? The number of terms? You would plug in, let's explore that in a sec. Let's put both up here and see why that would be the same. Okay, so let's write an explicit definition here. So we would say a sub n is equal to a sub 1, which is 2, correct? Times by our r, which is 2, raised to the n minus 1. Now it wants us to find the 10th term. So let's plug that in, and then we can look and see what Josh is talking about here. So we have a 2 times 2 raised to the 10 minus 1, which is 9. Now think about this. Why does this make sense, everybody? Look, if we start with 2, and that's a sub 1, and I say find the 10th term, wouldn't we be multiplying by 2, starting here, multiplying by 2 9 more times to get to that 10th term? So the formula, look, start at 2, times by 2 9 more times makes sense. Do you see it? Yeah? You do? You don't? You don't. Let me say it one more time. Starting with 2, if I say find the 10th term and we know we're multiplying by 2, starting here, find the 10th term. If I multiply by 2 9 more times, that will put me out at the 10th term. Because I started here. Started at 1. Does that make sense? So the formula makes sense. We start at 2. We're timesing by 2 9 more times. Because what's 2 to the 9th power by definition? 2 times 2 times 2 times 2, and so on to 9. Okay, so just trying to make it make sense for everybody because it's easier to remember in the future and it makes sense. So Josh, you're saying you're asking me 2 to the x worked as well? 2 to the, and then you plug it in as what? 10? For this one, it does. You're right. So he's saying if you plug in 10, that would work, because isn't this a 1 and this a 9? So when you multiply, you add. So it is, this one's working out nice and pretty, but they won't all work out that way. Why are they working out the same here? Because it's the same base. So they won't always be the same base. Yeah, valid question. Really good question, actually. Okay, sweet. Let's go on. Let's do number 11. Find the 10th term. So you'd say to yourself, I'm going to plug this into my explicit formula, which allows me to find any term in a sequence. For geometric, it would be a sub 10 is equal to a sub 1, which is 1, times by the common ratio. 9 divided by 3 is 3. 3 divided by 1 is 3. So we're doing 1 times 3 raised to the 10 minus 1. Does everybody agree? So that'd be 1 times 3 to the 9th power, right? Which makes sense. If I start with 1 and need to get out to the 10th term, I'm going to be multiplying by 3 9 more times. So we get what? 82. Perfect. Good. All right. Let's do number 12. Same idea, though. We'd say a sub 10 is equal to a sub 1, which is negative 2, times by our common ratio. Negative 18 divided by 6 is negative 3. 6 divided by negative 2 is negative 3. So our common ratio is negative 3. You're going to want to put that in parentheses in your calculator, or else you might get it wrong, because this negative is also raised to the 10 minus 1 power. So number 12 would come out to be, looks like 39,366. So make sure you use parentheses. You all get it? Okay, I want you to spend some time now doing 1 through 19. So on number 10, we never finished out calculating that, and we should have got 1024. So this one takes more in-depth thinking. Let's see if you can do it. They're not always going to be that easy. I'm going to extend the knowledge on the test, giving a little bit harder problem. So it says, given that the second term in a sequence is 6, and the fifth term in a sequence is 48, first of all, what's the common ratio? And then what would the 8th term be? So this one's more in-depth thinking, but we do know how to do it. So there are a couple ways we could tackle this. First of all, we could kind of set ourselves up kind of a picture. Careful, it says, given that the second term, we don't know a sub 1, do we? We do know a sub 2. Our second term is 6. Then we don't know a sub 3, a sub 4. Don't we know a sub 5? A sub 5 is 48. It says, what is the common ratio? So, once again, I heard this group talking about one similar to this. They said, well, let's just set ourselves up a true statement, like Miss Christensen said yesterday. They were doing awesome over there. So you're right. What would my true statement be? 6 times something equals this, correct? Times something again equals that. Times something again equals that. So my true statement is 6 times question mark times question mark times question mark equals 48. So we have 6 times question mark cubed equals 48, don't we? Divide by 6. So then question mark cubed equals 8. So question mark is 2. Cube root both sides, question mark is 2. So now we would use our formula. So we would say it wants the 8th term. So we'd go off to the side and say, okay, a sub 8 is equal to a sub 1. What is a sub 1? 6 divided by 2 is 3. So then we would say 3 times by, we just found our r was 2. Now raised to the 8 minus 1. So everybody see how it took a little bit of thinking. You're not always going to be given just a straightforward problem. You might have to think a little bit. And be careful on how you tackle it. So we would have 3 times 2 raised to the 7th power, which is 384. So the 8th term would have been 384. All good? Okay, cool. Is everybody finished on the problems 10 through 19? Okay, let's do number 20. There are 2 ways to do number 20 together. Once again, the one way is kind of easier in a sense, but then when you do harder problems, it won't work. So let's show you way number 1. So let's call this x, and let's set up a true statement. Isn't it true to say 16 divided by x will be equal to x divided by 4? We have a common ratio every time, right? This divided by this will be the same as this divided by this, right? So 16 divided by x will be equal to x divided by 4. Then solve for x. So when we cross multiply, multiply 4, right? Multiply x. So then we have 64 equals x squared. So x is equal to, yeah, plus or minus 8 though, right? Square root of 64 could be positive 8 or negative 8. So that was x. I'm going to erase that. So we could have got plus or minus 8 here. Now, here's the way I would really probably do it, think through it this way better, just because if it's a harder problem, it won't always work that you just have one missing value. You couldn't call this x and x. So once again, instead, let's pretend like we didn't know that and set up a true statement on way number 2. 4 times something times that something again equals that. 2 somethings in this problem. So we have 4 times question mark equals 16. So that's 4 question mark squared equals 16. Question mark squared equals 4. Does everybody see what I'm doing? Solving for question mark. So question mark is equal to plus or minus 2. So we're either multiplying by positive 2 or negative 2. So that makes sense. Look, 4 times positive 2 would be 8. Times 2 again would be 16. So 8 could work. Then 4 times negative 2 could be negative 8, right? Times negative 2 again could be 16. That's why we really don't know if it's 8 or negative 8. Either one, however you want to find it. Now what we did, you're going to see these words sometimes, is we found a geometric average. So that's called a geometric mean. So if I say find the geometric mean of 4 and 6, you would just set it up like this and solve it however you want. The geometric average. Okay, do problems in that section 20 through 28. And once you've done those ones, try this one to make sure you can extend your knowledge to a harder problem. So we have this, correct? So then question mark equals plus or minus, I think it's 3, is it? Okay. Yeah, that is 3. Okay, so with that being said then, we're going to have a couple different answers here. Filling this in, we would have to say, okay, 4 times 3 is 12. Couldn't that mean this is plus or minus 12? Times plus or minus 3, so 12 times 3, obviously, right? Plus or minus 36, yeah? But it should just be plus 36. You're right, not minus. Because no matter what, if we multiply, yep, it's going to be just plus. Does everybody see why it'd just be plus? Yeah. If we multiply by a positive 3, it's going to be positive 36. If we multiply a negative by a negative, it would be positive 36. Good point. And then 36 times 3, right? So then we're back to, once again, plus and minus 108. Good point, Tanner. Okay, awesome. Are we finished with that section? So now geometric series they have a geometric common ratio, but we're going to be adding them, the sum. Series means sum. So now the first thing we're going to talk about is a finite geometric series. So just a reminder what finite means. Finite means you know when to start adding and when to stop adding. If it's finite, you can add it up. You can find the sum because you know exactly when to start and stop adding. So this would be the formula for a finite geometric series. A sub 1 times 1 minus r raised to the n divided by 1 minus r. It's always smart to throw some extra parentheses around that, and then you should be good to go. So this is already on your little worksheet, so now we'll just apply it. So this is what I call, it's not that bad, but I call it the ugly formula, just to keep them separated, because there's a pretty formula we'll use for infinite in a minute. So this is what I call ugly, just because it's bigger. Harder to type into our calculator, but it's still not that bad. So R is the common ratio, A sub 1 is the first term, and then obviously N is the number of terms we are summing up, just like with arithmetic. Are you all good? Let's apply the formula here. You've already got this on your formula worksheet. Okay, here we go. Look at number 1. Now, everybody look. Looking at the problem, I always have students say to me, okay, 40, 20, 10, good to go, but then there's a dot, dot, dot. This is infinite. Well, actually, though, in the instructions it says, find the sum for the specific number of terms. It tells you 10 terms is where we want you to stop adding. That makes it finite. We know when to stop adding, 10. So we will use this ugly formula here. So we say the sum of 10 terms is equal to A sub 1, which is 40 times parentheses 1 minus r. So let's see, what is our r? 10 divided by 20 is a half. 20 divided by 40 is a half. So our r is a half. You need to use parentheses around your r. So minus a half raised to the 10th power, close it again, divided by 1 minus r. As you go through, try to memorize the formula. You're going to need it memorized for the test. So now you would just type it into your calculator. Just kidding. 79.9. If you got that, then we're all good. Now think about it. Your sums should make a little bit of sense. So look up here. Think about it. We're adding up 40 plus 20 plus 10 plus 5, correct? Plus so on, everybody. Plus 5 halves, and so on. Now think about it. What's 40 plus 20 plus 10? That's 70. Do you see how we're almost to the whole sum? Well, it makes sense because as it gets smaller and smaller, the decimals we're adding in are littler and littler. So that does make sense that it would reach 79.9 roughly. Everybody see? Okay, sweet. Do 1 through 6 go. Because on your worksheet, they make it too easy on you, and it will not always be that easy. So let's make sure we're good. So everybody, on your worksheet, they make it easy on you. They say to you, sum up 10 terms, so you can just plug it right in. But I might not give you something and tell you how many terms you are summing up. You have to figure that out. So everybody look. It says, what is the sum of the finite geometric series? Here's A sub 1, and looks like we're going to add till we stop here at A sub n, correct? We need to know for our formula how many terms we're summing up. So this is going to be similar to those arithmetic ones where we have to do some algebra first. So we would use our explicit formula, plug in what we know, so that we can find out what n is. If this is A sub 20, we're summing up 20 terms, right? So let's do some algebra using the explicit formula. So we'd say A sub n, which is 3072, is equal to A sub 1, which is 3, times by, yep, so 12 divided by 6 is 2, 6 divided by 3 is 2, so times by 2, raised to the n minus 1, right? Okay, so everybody, make sure you are, grab your calculator if you need it. What would be my next algebraic step? Okay, divide both sides by 3. So then we have 1024 is equal to 2 to the n minus 1. Now careful, algebraically it would not be appropriate to divide by 2. This is a base with an exponent n minus 1. Unfortunately, in this unit, we have not yet learned how to solve by using logarithms, which we'll learn later. So we would have to solve by setting up a true statement. So what we're going to want to do to solve for n is we're going to want to put this as a base 2 instead. So 2 to what power equals 1024? Figure it out. Ready, go. 2 to what power? How can I rewrite this as base 2? 10, you said? So they just sat and tested it out or figured it out, right? 2 to the 10th power is equal to 2 to the n minus 1. Now look, Whatever we solve for n to make this a true statement would be our answer. So my true statement would be 10 is equal to n minus 1. So n is equal to 11. Everybody good? We'll learn later how to solve with logarithms, but we won't get there for a little bit. So this is a sub 11. So we know we're summing up 11 terms. It's finite, so we can now plug it into our formula. 3 times 1 minus 2 raised to the 11th power divided by 1 minus 2. All good? So then the sum would be 6,141. Okay. Let's look at another one. They sat and tested it out. They did 2 to the 3rd, 2 to the 4th, 5th, 6th, 7th, 8th, 9th, 10th. Boom, found it. You just had to test it out until you found it. Because we wanted them in the same base, because then we could just solve using the exponents. Yeah, good question. All right, so let's do this one. Everybody, looking at this one. Just this one, let's see, you guys try it. The reason I'm having you try it is because there's a lot of negatives and people mess it up. So try it. Ready, go. With this? So your equation should say S of 6 terms is equal to A sub 1, negative 15, times 1 minus, isn't it negative a half? That's what gets people. You've got to, if your R is negative, you've got to put in your negative in parentheses as well. Oh, it's negative 2. No. Yeah. 60 divided by 30 is negative 2. Oh, man. Oh, man. Bless my little heart. Minus 2 raised to the 6th power, and then all over 1 minus negative 2. Just a lot of negatives to be careful typing in, really, is my points with showing you this one. So you should have got 315. Okay. Are we good? Okay, looking at this one, would you be able to extend your knowledge? So given it instead in summation notation. Well, isn't it in summation notation the same thing as having it written all out? Now, careful, this one will get you. How many terms? We know it's geometric. And one more thing, how do I know it's geometric? Look at the formula here. We're starting with 4, and aren't we timesing by a value this many times, however many times we want? Yeah. So this is what a geometric explicit formula will look like of this format. Does everybody see? A sub 1 times R raised to the n, or n minus 1, geometric. So because it's geometric, we would use this formula. So if I said no calculator, how many terms? This one gets people. 21 terms. Now think about why that makes sense. On this one, we're plugging in 0 first. Plug in 0, then 1, 2, 3, up to 20, so that's 21 terms. How can I just do that using algebra? 20 minus 0 plus 1. So we'd say the sum of 21 terms is equal to A sub 1. How do I find A sub 1? Don't you plug in the lower limit? So that's 4 times 1/2 to the 0 power, which is, so that's 4 times 1, which is 4. And then 1 minus, what's my R? Now think about it. What are we multiplying by each time? 1/2. Are we starting with 4 and timesing by a half? However many times we want. So our R is a half raised to the 21 power divided by 1 minus 1/2. Okay, sweet. And then we would type it in, and we will get 7.99, which is pretty much equal to 8. Are you all good with that? You can extend your knowledge to harder problems, different problems. Okay. Okay, now let's talk about the sum. This is where it gets really interesting. So we knew with an arithmetic series, if we have an infinite arithmetic series, we cannot find the sum. However, it's very interesting. In a geometric infinite series, there are times when you can find the sum and times when you can't. And I'm going to make sense of this. So there are infinite geometric series where you can find the sum. So everybody think about it. It says right here, the terms of a geometric series grow rapidly when the common ratio is greater than 1. So for example, if I start with 2 and I'm multiplying by 2, Aren't I getting larger and larger? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, and so on. That's getting really, really large. Am I ever going to stop getting larger and larger? No. Okay, moving on. Likewise, they diminish rapidly when the common ratio is between 0 and 1. So let's say that the common ratio is a half. If I start with 10 and multiply by a half, I get 5, right? Times by half again, something smaller. 5 halves times by half again, it's smaller, smaller, smaller. All of a sudden, finally, I've cut this up so many times, it's so small that it's basically 0, right? So that would be where we are able to find a sum. So if it is growing rapidly, that is when your R is a whole number, then it's growing rapidly and you cannot find the sum. We would not know when to stop adding. Can't sum them up. Then if your R is getting smaller and smaller, that's why I say fractions. Fractions, I should say less than 1, between 0 and 1, and it's getting smaller and smaller, and it's going to approach 0. So you can finally, eventually find the sum. So you can find the sum. No, but what we're adding will basically be 0, right? So if I take a piece of bread and I say, okay, I need you to add up all the pieces of this bread. Now I cut it in half again, so I have a couple pieces of bread. So now I have half a bread and a half a piece of bread, right? Cut it in half again. Cut the bread again. Cut the bread again. Now we're chopping up the bread finally where there's no bread more to chop up, right? Because it's so small. I'm chopping it so small. Can't I now sum up all those pieces? Because basically there's 0 now. That kind of put it in perspective. Yeah, so what you're chopping up gets closer and closer to 0. So at a certain point, you're basically adding 0. So it's called, they use a special word here. So everybody, this is called, if you can't find the sum, it's called a diverges. Divergence, how I remember that word is divergent in the movie. In fact, you've read the book, but who reads? Just kidding. I'm just kidding. So in the book, in the movie, divergent, it's like the people who go crazy or kind of out of control. If it's getting larger and larger, it's going to get so large, like you're never going to be able to add it up. That'd be crazy to try to add up all those numbers because you'll be adding forever. So divergent is bad. You cannot find the sum. But if it's getting smaller and smaller, eventually you're approaching 0, correct? You're approaching adding up 0. So that's like an asymptote. So if you can find the sum, if it's getting smaller and smaller, it's what's called converging to a sum. It converges, converges. So it converges towards a sum. So the more you add up, the closer and closer it gets to that sum. So, and the nice thing is here's the formula. So if it's infinite and geometric and you can find the sum, if it's getting smaller and smaller, you can find the sum, you use what I call the nice formula or the pretty formula. Look how easy it is. You take a sub 1 divided by 1 minus r. So we almost like infinite geometric series. Does everybody kind of understand? It's only if you're getting smaller and smaller. It's easier for me to remember it like that because once again, it's going to eventually get so small that you're adding up 0. You have those 2 words written down, diverges and converges. Okay, let's do these examples. So, like I just said, here's going to put it into perspective for anybody who's still a little leery about this. So look at this example. This is an infinite geometric series. 2 becomes 4, becomes 8, becomes 16, becomes 32. Isn't it getting larger and larger? Well, I'm not going to know when to stop adding because we can continually get larger and larger. So there is no sum, it diverges. Now our R was getting larger and larger, so they'd say it's greater than 1. Now look at this example. 2 plus a third plus 18 plus 1 over 108 plus 1 over 648. Isn't it getting so small that eventually we're pretty much adding 0? The smaller we get, the more we're adding just basically 0. So that is now converging towards a sum because you can add all these up, and the more you continue to add, the more close you get to converging towards this sum. At a certain point, they say, it's basically 6. Let's call it 6. And that's where that answer comes from. Now, one thing to notice, I had to say look at the absolute value of R because, for example, if we're multiplying by -2, that's still getting larger, but on the negative scale. So we would not be able to find the sum. Does everybody get what I'm saying? So you can't say Negative 2 is less than 1, so we can find a sum. Because if we multiply by negative 2, isn't that just going to be larger in the negative direction? And are you ever going to stop adding in the negative direction? No, because it's getting larger in the negative direction. Do you all understand what I'm saying? So if we were trying to use this rule, we would not look at negative 2. We'd say absolute value of negative 2 is less than or is greater than 1, so we can't find the sum. Yeah. Okay. All right, here we go. Let's put this into perspective. All right. Now, if anybody, we're running like way too low on time for me to explain. This formula is the same as this formula now, and that's because if we're summing up an infinite amount of terms, wouldn't infinity be for n, everybody? Now look, if I plug in infinity here, look where this formula comes from. A half to the infinite power. Think about it. 1 to the infinity is just 1, correct? But 2 to the infinity is really large. 1 divided by 2 to the infinity power. Isn't 2 to the infinity a huge number? 1 divided by a huge number is basically 0. Now look, a sub 1 times 1 minus 0. Isn't that just a sub 1? So that's why we have a sub 1 over 1 minus r. Same formula. Okay, kind of cool. Here we go. Let's apply it. Number 8. Determine whether each infinite series diverges or converges. So it's really easy to think through. Just look at it. Is this getting smaller and smaller? Well, it's eventually going to be so small it's 0. So we can find the sum. So we'd say it converges to a sum of, well, let's use the formula for an infinite geometric series. So we would do a sub 1, which is 3 over 1 minus r. What's our r? That divided by that. That divided by that. Or what are we multiplying by? Yep, 1 minus a half. Now look, we have 3 over 1/2, don't we? Which is 6. So Adam, at a certain point, so the more you add up here, if we keep adding these up literally by hand, the more we add up, the closer and closer it gets to 6. So eventually it's so close to 6, we might as well call it 6. Does that kind of help? Second asymptote, very good questions. Okay, look at number 9. Can we find the sum here? 4, 2, 1. Are we getting smaller and smaller, everybody? Okay, so we can find a sum. It converges to what value? The sum is equal to a sub 1, which is 4, over 1 minus a half. Wouldn't that be, the sum would be 4 divided by a half, which is 8. All good. If it's getting larger and larger, you can't find the sum, it diverges. Okay, I'm going to give you a couple minutes to do 8 through 21. Everybody look at this. These two are on your worksheet. So it says evaluate each infinite series that has a sum. So everybody look, the sum from 1 to infinity, that's what makes it infinite. Now we would notice this is geometric. Why? Because it has the format a sub 1 times r raised to the n minus 1, right? So we'd say to ourselves, okay, infinite geometric series either do or do not have a sum, depending on if it's getting smaller and smaller or larger and larger. So everybody look, is our r, is 2/3, and that's our r, is it greater than or less than 1? Less than 1. So this is going to be getting smaller and smaller. So this will have a sum. It converges to the sum of, let's do the formula, a sub 1 is on top, which let's plug in our lower limit. 1 minus 1 is 0, so 2/3 to the 0 is 1, so 5 would be our a sub 1, divided by 1 minus r. Our r is 2/3, like we said. So then we would calculate it, and we get the sum is 15. And I even tested this out in theory. I wrote out as many terms as I felt necessary, and I started adding them. And as I did, that's really how it put it in perspective to me. The more terms I add up, the closer and closer I get to 15. So we're just going to call it 15. Because the more we add up, the closer we get. Okay, let's do number 29. So looking at this one, isn't this our r? Negative 2.1. Now, a lot of people will mistake this and say, well, that's less than 1. Well, no, it's getting smaller, yes, but largely. So this does not have a sum. So we would look at the absolute value. So 2.1 is greater than 1. So there's no sum because it diverges. Everybody good with how to do these? Okay, that is the end of the lesson. So just finish the worksheet.